Okay, good morning. So last time we have stopped in the middle of a proof of division algorithm for polynomials. So let's remind the statement of the theorem and conclude the proof. Division algorithm for polynomials over a field. Today this will be theorem 1. So let F be a field. And f of x, the polynomial ring, be polynomial ring. And then for a pair of polynomials, for f of x, g of x belongs to, which belong to f of x, such that g of x is non-zero. There exists a unique pair. There exists a unique pair there exists a unique pair of polynomials. Q of x and r of x. So here Q stands for the quotient and R stands for the remainder, such that f of x can be written as Q of x multiplied by g of x plus the remainder r of x. That's the first condition, and also that the degree of r of x, strictly less than the degree of g of x, and the degree of the something by which we take the quotient. Okay, so as for the proof, we went over the existence part. Existence proved last time. So let's just briefly talk about the uniqueness. It's rather short. And then we will discuss the applications of this theorem. So now suppose that this quotient and the remainder polynomials are not unique. Suppose there exists two pairs. The first one we'll call Q1 R1 of x and Q2 R2 of x, such that f of x can be written in the above form, namely that this is Q1 of x multiplied by g of x plus the remainder term r minus 1 of x, and at the same time is the same as Q2 of x times gx plus r2 of x. So where both the degree of r1 of x, 1 of x, is less than degree of g of x. And the degree of r2 of x is less than the degree of g of x as well. Okay, so let's call the degree of g of x to be m. And let's look at the following. So from this, if we just equate both sides and combine the terms in front of gx on the left-hand side, what we'll get is that gx multiplied by q1 of x minus q2 of x must be equal to the difference of the reminders, right? R1 of x minus R2 of x. So what we get here is that the degree of this guy, is greater or equal than m, right? Because if you have a polynomial over a field, so deg g of x equals m, right? And you multiply it by any other non-zero polynomial, then sure enough you get something which has the degree greater or equal than m. But on the other hand, by the assumption, the degree of this guy must be must be strictly less than m. So in other words, there cannot exist two distinct pairs of quotient and remainder. Okay, sorry for running out of space on this slide. Okay, so now this theorem is very similar, of course, to what you've seen for the division of integers or natural numbers, division with a remainder. And today we will have a lot of kind of parallels between the two stories. That's not a coincidence, of course. But before, let's go over a few examples and corollaries of the theorem. Okay, so now the quotient of one polynomial, quotient and remainder of one polynomial by the other can be computed using the division algorithm, which is essentially identical to the division algorithm for integers. So let's take field to be the field with two elements, z2, and let's look at the two polynomials. So the first polynomial will be x cubed plus 1, and the second polynomial will be x squared plus x plus 1. And let's divide one by the other. So we start with x cubed plus 1, right? And we divide it by x squared plus x plus 1. Okay, so first we compare the two leading terms, this one and this one. And in order to cancel them, we have to multiply x squared plus x plus 1 by x, right? Okay, so we multiply it x squared plus x plus 1 by x. And from x cubed plus 1, we subtract the following polynomial, x cubed plus x squared plus x. So what we obtain is that it is minus x squared minus x plus 1. But of course, since we're working over z2, minus x squared is the same as x squared plus x plus 1, right? Well, then we compare again the leading factor of this polynomial with x squared, right? and see that we have to multiply it by 1 to subtract. Okay, so as a result, we obtain the following thing. We obtain that x cubed plus 1 can be written as x squared plus x plus 1 multiplied by the quotient, which is x plus 1, and plus remainder, which in this case is 0. So this is the quotient, q of x, and this is a remainder, r of x. Okay, and because we're working with polynomials over a field, right? When you compare this highlighted by yellow leading terms, you can always find a factor by which you have to multiply your polynomial g of x to cancel the leading term. Remember that this kind of algorithm wouldn't literally work when when there exist non-invertible elements in the ground string. So that's why we restrict ourselves to a field. That's that specific kind of property used here. Okay, so let's talk now about the corollaries of theorem 1, and there will be a bunch of them. And the first corollary corollary 1 would be the following. So that an element A of a field F is a zero of polynomial f of x over this field F, if and only if and only if x minus a is a factor of f of x in this polynomial ring. By factor, I mean that if we divide, we that we can factor f of x as x minus a times something. Okay, so the proof is essentially straightforward. So proof. So what do we get? So by theorem 1, f of x can be written as, we can divide f of x by x minus a with a remainder, where the degree of this remainder is less than 2. So it's actually a constant polynomial. So it's q of x multiplied by x minus a plus c naught. Oh, is less than 1, sorry. Okay, so then of course we get that f of a equals to 0 if and only if c naught equals to 0, right? Okay, that's kind of a fairly simple corollary, but it immediately implies the other corollary, corollary 2, that a polynomial of degree n, polynomial of degree n can have at most n roots, can have at most n roots. As you all know, it might have less, and again, the proof will be divide f of x by x minus ai for all roots. Each time it must be divisible, right? By corollary 1 it's divisible. Corollary 1 it is divisible by all of them, and each time degree drops by 1. Time degree drops by 1. Oh, at most by 1. No, exactly by 1, sorry. This is working. Okay, so that's fairly easy. You've been familiar probably with this corollaries long before you were enrolled in the abstract algebra class. But now, kind of the interesting thing is that we can study some number theory questions using polynomials over finite fields. So we can study some number theory questions using polynomials over a field. And kind of the best illustration of that, which is fairly simple, would be the corollary 3. So let F be a field, and let G be a finite subgroup of the group of units. Be a finite subgroup of group of units F cross, which in the case of a field is just F minus, anyway, I'll write this in the proof, this formula, which is just all non-zero elements of a field actually. Then the theorem says that G is cyclic, and G must be cyclic. Okay, and the proof would go as follows. So we know that G is abelian, and finite. So by the fundamental theorem of finitely generated abelian groups, it must be isomorphic to a product of cyclic groups, right? Z sub P1 to K1 cross all the way Z sub Pn raised to the power Kn, where P1, Pn are primes. Okay, so let's look. So our argument will be basically on the order, will be based on the orders of all elements of a group G. So let's look at the M, which is the least common multiple of this P1 to the K1 all the way to the Pn to the Kn, right? And that for all elements, for all, let's make it as a first bullet. For all elements AI, which belong to the cyclic group Z Pi to the Ki, we have that AI raised to the power Pi to the Ki must be 1. As a corollary, AI raised to the power M must be 1, right? Because M is divisible by Pi to the Ki. Okay, so then what do we have? As a corollary, for every element alpha, or let's call it A, to be A1 all the way to AN in G, we have A raised to the power M, and in the direct product that would be equivalent to raising all the components, AN to the M, equal to 1. I'll say this is 1, 1, 1, which is, of course, an identity element of the product group. Okay. So this gives us the following statement. Then every element A in G is as 0 of polynomial x to the m minus 1, right? And let's move and every element A in G we move it to the next slide. Sorry for this pause. Is a 0 of polynomial x to the m minus 1. So that's an element of the polynomials. One. Okay. But okay. But then what we know is that so we can think of this element as a polynomial over a regional field F. Recall that we started that G is a group of units. G is a finite subgroup of a group of units. So let's just think of this polynomial x to the m minus 1 as a polynomial over a regional field F. Okay, so but kind of this G has only in total the P1 to the K1 multiplied by the P2 to the K2 all the way to the Pn to the Kn. So G has this many elements. And by corollary 2, x to the m minus 1 can have at most m distinct roots in F. So from here we conclude that the degree of this polynomial should be greater or equal than the number of roots, right, we have. Pn to the Kn. And at the same time, kind of, what's the m? It's the LCM of P1, Pk. So let's call this equation star. So same time by an equation star, we know that m is less or equal than P1 to the K1 all the way to the Pn to the Kn. So m actually equals to the P1 to the K1 all the way to the Pn to the Kn, and that's the order of G. And that's essentially the proof of our theorem. So because the order of an element A, order of an element, you already used B. The order of an element which just consists of ones equal to M, right? Equal to G. So it must be a generator. So in fact, what we just proved is that there cannot be the number of factors in this Z, and the product of cyclic groups cannot be more than one. So G is cyclic. Okay. So any questions about this theorem? Okay, so kind of, yes?
That all the primes in the factorization only appear once, essentially?
Yeah, exactly. Yeah. So n cannot be greater than 1. Exactly. That's right. Because otherwise, kind of the largest order of an element would be less than the order of a group. So.
Well, can we have it like Z2 times Z3 have two different primes?
No. Oh, sorry. Yeah, but it's cyclic. You're absolutely right. Because Z2 times Z3, it's kind of Z6, it's cyclic group. Sorry, yes, I kind of I rushed into this because let me just say, so what we proved is that this is a generator of G. Yeah, correct. So there can be more than one prime, but this is the generator, so the group must be cyclic, which means that all these primes must be distinct. That's thank you. Okay, so now a particular case of this corollary 3, A would be the following. So let F be the finite field ZP, and G be the entire group of units. It's finite, of course. Be a group of units. Group units, which is finite. And let me stress that it was very important for this corollary that we consider a finite subgroup of a group of units. But when we have a finite field, we don't have any problems with that, right? So because the entire group of units is finite, then ZP cross is actually nothing. It's actually isomorphic to the cyclic group of order p minus 1. Well, you probably noticed that by solving the homework exercises already. That what you always get for the prime number is just a cyclic group. Okay, so this is just one of many applications for which you can use the polynomials over finite fields to solve various number theory questions. So any more questions about this? Okay, so now let's move on to the next topic, and let's talk about some generalities. Well, generalities is about factorization, and irreducible elements. Well, okay. First of all, so let's for a few moments, let's forget about the ring of polynomials and just talk about the general commutative rings with unity. Definition, that will be definition 1 for us today. So let R be a commutative ring, be a commutative ring with unity. With unity 1 in R. That we say that A divides B. We say that A divides B if there exists a quotient C in R such that B equals to AC. To AC. Well, pretty much what you would expect, you know, from the word divides, right? Okay, so a couple of examples here would be as follows. That's probably example 2 already. If we have a unit, right? If we have a unit, belongs to R is a unit. Let's actually even say both ways. So X in a ring is a unit if and only if it divides the unity. Spacing is awkward here. Is a unit if and only if X divides 1. Okay, so let's look at example 3. So in example 2, we kind of describe all elements which divide 1. In example 2, let's go back to our polynomial ring over Z6. Z6 is not a field. Not a field. It has 0 divisors. And not every non-zero element is invertible. Still, we can talk about when one polynomial divides the other, but we will notice some pathologies. Like, for example, 3x plus 2 divides x. And recall from one of the lectures that 3x plus 2 multiplied by 2x plus 3 is actually equal to x in Z6. So according to our definition, 3x plus 2 divides x here. Okay, so this is kind of just to remark why our basic intuition works better for polynomials over a field. Right? Okay. So now we want to introduce the notion of irreducible elements. So we know that some of the polynomials, and for example, polynomials over reals, etc., they cannot be presented as essentially non-trivial product of other polynomials, right? Of strictly smaller degrees. And we know that in the ring of integers, the prime numbers cannot be presented as kind of non-trivial product of other integers. So the formal definition for that would be as follows. That will be definition 2. Let D be an integral domain. D be an integral domain. So this is a commutative ring with unity with no 0 divisors now. Then we say that an element P in D is irreducible of D if for every factorization of this element P as a product of two other elements, A, B, and D, either A is a unit or B is a unit. Either A is a unit or B is a unit. In other words, there is no non-trivial factorization. Of course, for every element, you can present it as some other element multiplied by a unit, but that's okay. So the prototypical example for an irreducible elements is the notion of a prime in the ring of integers. Let me leave the definition. So prototypical example 4. We know that Z is an integral domain, domain then the group of units z cross, it just consists of two elements, 1 and -1. So these are the only elements which have multiplicative inverses. And then plus minus p for prime p, for prime p are irreducibles of z. And of course, all other elements are reducible. Other elements are reducible. Reducible, we say that the elements are reducible if they are not irreducible, of course. Okay.
Why didn't we define it by saying that either A or B has to be a unity?
Well, because here's the point. If you look here, right? Let's take 7, right? We can write 7 as -1 multiplied by -7. This is not a unity. And this is not a unity. So if we will require that there is essentially no factorizations at all, we will run into pathology even with a ring of integers. But we kind of know that, 7 and -7, they are essentially the same prime, right? And that's because they different from each other by multiplication. I mean, they differ from each other by multiplication by a unit. And here, in order to account for this case, we have to require that either A is a unit or B is a unit. Does it clarify the question?
Oh, yes.
Okay, thank you. Yeah, but that's important. Thank you very much for asking. So we need to allow for factorization as a unit times something, because even in the ring of integers, right, we know that primes can be factorized of something, of something which is not just 1 times this prime, but it will always have the property that one of the factors must be a unit. Okay, now let's talk about the example of Gaussian primes. So that was, and cross ref to homework. So Gaussian integers z adjoint I. So this adjoint here is for now has nothing to do with the polynomial ring. Actually it does, but for us this is just a notation. So this is just a notation for the Gaussian integers. And we know that it is an integral domain. There is no zero divisors there. And kind of one can prove that the following elements are irreducible of z I. In other words, Gaussian primes. that this is plus minus 1 plus minus I, plus minus 1 plus minus 2I, plus minus 2 plus minus 3I, etc. And here's kind of a neat thing is that not every irreducible of Z, irreducible of Z is irreducible of Zi. And for an example of a prime which actually can be factored over the Gaussian integers, the first example is 5. So 5 can be factored as 2 plus I multiplied by 2 minus I. So it is not a Gaussian prime. Not every usual prime is a Gaussian prime. Okay, this brings us to the following example for the ring of polynomials. So that will be example 6. That the ring of polynomials in one variable is an integral domain. What is the corresponding ring of units? So that's the question to the audience. Can you describe the corresponding ring of units? So what kind of polynomials are, what polynomials with integer coefficients are invertible? So definitely none of the polynomials of degree greater than 0 can be invertible, right? Because if you multiply it by any other polynomial, you can always get the higher degree. And so this is actually coincides with the ring of units of Z. So it's minus 1 and 1. Oh, sorry, with a group of units of Z. Okay. So we have that this is an integral domain, and this P1 of x, which is x squared minus 2, and P2 of x, which is x squared plus 1, are both irreducibles, both of Zx. And kind of the next take is that kind of element which is irreducible, element which is irreducible of a subring can be reducible in a larger ring. So one example was when we factored the prime number 5 as the product of 2 plus I and 2 minus I. But in the polynomial ring, if we look at these polynomials P1 and P2, so let's look at x squared plus 2 and x squared plus 1. Okay, so over the ring of polynomials with rational coefficients, both are irreducible. This is irreducible and this is irreducible. Well, but the ring of polynomials with rational coefficients is a subring of polynomials with real coefficients.
Wait, are
Yes.
you doing x squared minus 2 instead of plus 2?
Minus 2, yeah, thank you. Yep. As a matter of fact, this one will also be irreducible, but thank you. Okay, so now when we work over the reals, x squared minus 2 becomes reducible. And thank you for the comment, because here it will be important that it is x squared minus 2. But this one is still irreducible. And if we kind of look into the ring of polynomials with complex coefficients, of course, both r becomes not irreducible. So when you say that some kind of polynomial is irreducible, it is important to remember that you have to specify in which ring it is irreducible. Okay. So let's move back to polynomials over a field. So let's conclude our generality back to polynomials over a field. The short lemma would be as follows. So let F be a field, then the group of units of the polynomial ring with coefficients in F is just 1 and minus 1. Only two polynomials are invertible. And kind of sketch of the proof. Sketch of proof. It's essentially based on the fact that the degree of the product of two polynomials, p of x and q of x, is equal to the degree of p of x plus the degree of q of x for all non-zero p of x, q of x, and this polynomial ring f of x. And this is actually a kind of this is really why this is actually why we don't define a degree of zero polynomial. Because you will run into pathology with this formula. Okay. So now an alternative kind of, let's say that this is definition 1a. Definition 1a. And this is particular case, well, let's say it's alternative definition 1. Alternative version of definition 1. One specific to the ring of polynomials over a field. Specific to r equals f of x. Okay. Let F be a field. So now let F be a field. Then an unconstant polynomial. And polynomial f of x in this polynomial ring of polynomials in one variable is irreducible over the field f if it cannot be expressed, if it cannot be factored as f of x equals to g of x multiplied g of x multiplied by h of x, such that degree of g of x is strictly less than the degree of f of x, and degree h of x is strictly less than the degree f of x. So we say that the polynomial is irreducible if we cannot factor it as a product of two polynomials of strictly smaller degrees. And as you might see, this is just a particular case of our definition 1 for the ring of polynomials over a field. Okay, now in general, there might exist irreducible polynomials, kind of in principle, there might exist irreducible polynomials with there might exist reducible polynomials which have no roots. But this cannot happen in the degrees 2 and 3 due to the following theorem. No, that's not theorem 1. It's theorem 2, right? Because we repeated the theorem from last time. Okay, so let f of x be a polynomial. X be a polynomial of degree 2 or 3. Be a polynomial of degree 2 or 3. Then f of x is reducible. Then f of x is reducible over f if and only if it has a 0 in f. If and only if it has a root in f. Well, for the proof, the opposite implication essentially follows from division algorithm. Follows from division algorithm. So suppose it has a root, then it's definitely divisible by some linear polynomial, right? And because the degrees of the product of non-zero polynomials over a field, they just add up, then this gives us the statement. Now, the direct implication is actually much more interesting. So let's assume that f of x is reducible. Is reducible. Well, so f of x can be written as product of a of x multiplied by b of x. And degree of a of x must be strictly less than 3. Degree b of x must be strictly less than 3 as well. Now the degree of a of x times b of x equals to the sum of the degrees, right? Degree a of x plus degree of b of x. 2 or 3. So at least no, kind of what we should write here is that this degree is strictly less than degree of f of x, and this degree is strictly less than the degree of f of x. So at least one of them of a of them must be of degree 1. Degree 1. Now, without loss of generality, we can assume that a of x equals to a1x plus a0, and then kind of minus a0 over a1 is a root of a of x, and hence of f of x. Okay, so why do we care about these irreducible polynomials? It's precisely because they play the same role as prime numbers play in the ring of integers. Namely, we can factor every polynomial as a product of irreducibles in essentially unique way. Essentially meaning that you can have this freedom of multiplying factors by some units. Like in the example where we represented 7 as product of -1 and -7. Okay, this essentially brings us to the idea of unique factorization domains. So today we will just give the definition, and we will talk more about more details in about 2 weeks. So that will be definition 4. So common abbreviation is, by the way, UFD. An integral domain is called a unique factorization domain. A unique factorization domain. If the following 2 conditions holds. So the first condition would be that every element x in D, which is neither a 0 nor a unit, which is neither a 0 nor a unit, can be factored into the product of finitely many irreducibles of D. Can be factored into the product of finitely many. Product of finitely many irreducibles of D. And the second part is that this factoring is essentially unique. But again, because we have this annoying units, we have to be careful and formulate it as follows. So if x equals D, and x can be written as a1 all the way to an, or as b1 product all the way to bm, are two such factorizations. Two such factorizations. Then first of all, m equals n, and b1 bm can be reordered, can be reordered such that ai is just bi multiplied by ui, where ui is a unit. Now, this means that factorization is essentially unique. And essentially means that, of course, you can reorder the factors and you can also multiply them by the units. So kind of silly example of a unique factorization domain is a field. Example 6. Oh, wait a second. ui product of finitely many irreducibles. Okay, good. Did I say this? Let me look. Oh, that's an important part. That's an important part. Sorry, I didn't mention it here. I apologize for that. That p t is irreducible, and of course we should assume that p is not a unit. P d, which is not a unit. Likewise, for the primes, we never call one a prime, right? Okay. So, and this brings us to the following example. So let f be a field. Let f be a field. Then it is a unique factorization domain. simply because there is no elements which are neither 0 nor a unit. Okay, and however, the more sophisticated example of a unique factorization domain is precisely the ring of polynomials over a field. Theorem 3. We won't really give a full proof of that theorem today. We will return to it when we will come to the notion of prime and maximal ideals in exactly a week. But we will formulate it during this lecture. So let F be a field, then f of x is a UFD. So in other words, every polynomial, f of x in this polynomial ring can be factored into the product of irreducible, of irreducible polynomials, and this factoring is essentially unique, and this factoring is unique up to reordering factors and multiplying factors by units. Up to ordering factors and multiplying factors by units. Okay. Now, the proof of the existence part is rather easy. Existence is easy. So basically by induction in degree of the polynomial. Induction in degree of a polynomial. Now, basis of induction. Basis of induction is the following. So kind of non-zero polynomials of degree 0, non-zero polynomials of degree 0 are units in f of x. In other words, the set of units of f of x cross is nothing, just f cross. So non-zero constants, right? Of course, they are invertible over a field, and none other polynomials are invertible in f of x. Now, linear polynomials are always irreducible. Always irreducible, right? So hence they also can be factored into the product of irreducible polynomials, meaning itself. And this factoring is, of course, unique. There is no way to factor linear polynomial as a product of linear polynomial times something which is not a unit. Okay, so the step of induction would be the following. Assume that we have proved theorem 3 for polynomials of degree less than n. So let f of x be a polynomial of degree n. Let f of x be a polynomial and f of x and degree f of x equals to n. Now, there is essentially two cases, right? So case one, when f is irreducible. So case one, f of x is irreducible. Well, then we are done, right? We are done. Because we already factored it as a product of one irreducible polynomial. Now, case two, f of x is reducible and is the product of a of x, b of x, where degree of a of x is reducible. So here degree of a of x is strictly less than n, and degree b of x is strictly less than n. Then by inductive assumption, both a of x and b of x can be factored. Into irreducibles. Then so is f of x. Okay, so now the uniqueness part is actually quite hard. This is harder, and we return to it, when we discuss in a week. So we need maximal, and prime ideals. And then the proof. Then the proof will be quite short. Okay, So I will stop here, and I will be very glad to answer the questions.
I have a question.
Mhm.
Earlier you said for a field, the group of units of the polynomials over the field is 1 and -1, but
No, that was for Z. So let's scroll back. That's a great question. So that was the ring of polynomials over Z.
on the bottom of the page.
Oh, geez. Sorry about that. Yeah, that's a mess. Sorry, that's what happens when you hurry. You're absolutely right. Yeah. So of course, what I wanted to say is that this is the same as F cross, which is just F minus 0. Thanks. Thank you very much. Yeah. Any more questions? Okay, so then I'll just rejoin the session to save the video of the lecture, and we will continue with of SARS.